Okay. Yes, so let me update you about your grades, because each and every one of you should know where I'm at and what is my plan. So this is your class. As you can see, I'm grading per student and not per lab. So I'm grading horizontally. So I know you're waiting for your grade, but I want the wait to be worth it. So hopefully when you get the grade, you get all the labs together, okay? My purpose is to reach up to lab 4, but I'm not gonna stop. If you have lab 5 ready, I'm gonna continue up to lab 5. Why lab 4? Because I believe it's important to have everything before the midterm. Talking of midterm, it's gonna be on Saturday as you requested, because we found it very difficult to find a common time for all the sections. I'm talking my sections and other instructors section as well. It's gonna be Saturday, November 7 at 3 p.m. Let me know if you have difficulty with the timing. I'm gonna write it in an announcement to make it official. All right? Yes? Any comments? If you can turn your camera on, it will be beneficial for everyone. I will keep it to your choice. Okay? So it's up to you. If you believe that my internet connection is not great, let me know. I noticed that today at LAU, the internet connection was giving me some difficulties. So if for some reason I'm glitching or something, let me know. At home, I was better off with my internet connection. Do you have any questions related to Lab 5? The deadline is tonight, right? Which means you still have time to ask questions. Yes, Joe?
Yes, I have. Okay. Doctor, there is in the tables you have to calculate the average.
Yes.
We should calculate. We should also calculate alpha RMS, or no?
No, no. You will be surprised to see this lab very light in data analysis. Why do they want the average? Because did you notice, Joe, that T of the charging and the T of the discharge is a bit different?
Yes.
Yeah, because you will notice some different sources of errors. In the past, I tried my best to understand why T of the discharge is actually more accurate than T of the charging. I don't know if I'm right or not, but back in the past, I have this issue, and the difference was huge until we started using the power supply and not the batteries. The batteries were giving us a lot of sources of errors, because they don't have a constant push or a constant, output voltage. So now the charge and the discharge are basically close. But if I need to do any analysis about how does the increase in capacitance will affect the time and so on, I wouldn't look at T charge. I wouldn't look at T discharge. I would look at the median. So it's not really an average. If you really think about it, an average is the median of something you keep on repeating, like many trials, but if you take the charge and the discharge and take a mid value, this is not really called an average. So it's wrong to say it's an average, and it's wrong to do RMS anyway. Okay, now with rounding.
Yes, doctor.
Yeah,
sorry, for 5 you said we have to use the median between TC and TG. I will not say the average. Yeah. Also for the question 6, we should do like this.
Yeah. For all of these, if you want data for tau, take the average. Because it's wrong to take the charge. It's wrong to take the discharge. Take something like the mean between them. Okay?
Okay, dear.
Yeah. And yes, you will be surprised that they don't ask you to calculate any uncertainty, but it has a lot of conceptual. These are all conceptual questions, right? And conceptual questions are very important, a part of the objective of physics lab. Conceptual, discussing how a parameter affects something else, discussing linear relationships or not, finding constant ratios or constant products. This is not easy, and it's important. As I was talking with George a few minutes ago before you came, and with Maria probably, for the midterm, you would expect a lot of data analysis questions and a lot of conceptual questions, probably a question or two where you have data and you need to do some calculation, but not a lot because you have the course for that, So for the lab, it's gonna be more conceptual, like if you double the length of the pendulum, what happens to the period, for example. Okay, like this is conceptual. and a lot of data analysis, some of which are related to your data and some are general data analysis questions, like to round up to a certain number of sig figs and so on. Very, very similar to Physics 1, right? I was wondering how was the final exam for Physics 1, and I do remember that you guys had an issue with the percentile. You were so stressed because you couldn't finish the multiple choice on time, right?
Objective part was the more difficult part to finish it.
Really? Yeah, probably. Yeah. The objective or the subjective?
Objective, and not the MCQ. The MCQ were easier to finish than the subjective.
Really? Okay.
Yeah, I remember saying the subjective was the harder part. Yeah. I couldn't finish it.
Yeah. Probably the timing was tough on you. We will see. Probably we can communicate with you if you have a subjective part or not, and if it's MCQ or not. I know that a test should be a surprise, but to decrease the stress, probably we can describe it for you before you start. Okay? And probably we can tell you how many questions you have and how long you are given, so for you to be ready. Okay? All right, so any other question concerning lab 5? Is that lab 5 or 6? I'm totally confused because one section has to skip 1 week. So yeah, experiment 5. Any questions related to experiment 5? Please let me know before the deadline tonight.
All right. Yes, one question for number 5.
Yes.
In the table, there's capacitance.
Yeah.
There's a column for capacitance. Do we enter the ones that are the theoretical or the experimental?
Those?
No. Sorry, number 4. Which part?
Okay, so here you have T of the charge for the series connection. The series connection.
Yeah, there's also a missing column. I don't know. It's not on your document, but in ours there's a.
It is on the result section. Let me
see.
Let me have a look. Probably the result section is a bit different. Result number 1, and I hate this. I'm trying my best to be very careful when giving you the results because every time I'm confusing you. Okay, I'm opening the results. Okay, so again, for the series, this is what you're talking about, right?
Yes, correct.
Okay, Chris. So basically, Chris, you are not given C1, you are not given C2 as measured value. Those are nominal values, and you know this. In this experiment, I never touched the LCR meter, and I never did the measurement of C1 and C2. So you have no choice to find the capacitance for the series connection or the C equivalent of your circuit. You have to choose the nominal values because the measured values are not given to you. Let's say you come to campus and let's say you do the experiment. Here it's an open experiment, which means you will have the right to ask for an LCR meter and to do the measurements, and students in the past did it. So students in the past did actually ask for an LCR meter, and they said, I don't trust the nominal value, I want to take a measurement of my capacitance. And by the way, they discovered a big difference between the measured value and the nominal value. It was a great idea and it was very creative. So for this lab, Chris, I did not do the measurement for the measured capacitance C1 and C2. All you have is the nominal value, so you have no other choice. Did I answer your question, or you wanted something else?
Yeah, I think so. The thing is, because we can find it using tau equals RC, so we find C equals tau over R. Or we could do the addition of each C1 and C2 and C together.
I think no matter what you do, eventually you need to do it in item 6. In item 6, they want you to find C equivalent using the nominal value and C equivalent using your data and to compare. So I would say whatever you do in this table, it doesn't actually matter, since remember the lab report is an open-ended question, which means you would want to use this method, Maria would want to use any other method, so it's up to you. I don't want to limit you, Chris. So if you believe this is something that is interesting for you, do it and explain it in a line or two. I've decided to do this because probably this is more close. So the table is a template. You can add to it, you can remove from it, you know?
Yes, okay.
So for me,
Thank
why
you.
not? Why not if you want to use it from tau? And eventually you will explain it under item 6. Yes?
Okay, dear. Thank you.
All right. More questions related to lab 5 or probably 4 or 3 if you still have questions. I would want to discuss something related to lab 4 because I need to give you feedback. Can you please tell me again, while discussing the brightness of the bulb, how do you believe the brightness will vary? Due to what? Any ideas?
Which series or parallel connection?
Yes, so in series connection, you have a brightness. In parallel connection, you have a different brightness. But this difference in the brightness, it's due to what?
Power.
Okay, and how do you define power?
You mean intensity, Yvonne?
Okay, what do you mean by intensity? Because intensity for me, it could be the intensity of the current or the intensity of the brightness. So you mean the current.
Yes.
So
Yeah.
Ryan is saying brightness depends on the current. And Michelle, was it you, Michelle? You were saying that brightness depends on the power. So is it current or power?
It is both, since power is I times V.
All right, so Francesca is saying...
My doctor,
Yes, Ryan?
sorry, did I interrupt anyone?
No, no,
Because
no.
it's lagging. So.
Yeah, it's okay, say it.
I'm saying, usually for a light bulb, depends on the current, also on the resistance in it, because then also coming and receive push them.
All right, so as I can see that you guys have a lot of ideas, Francesca, Ryan, and Michelle, and most of everyone, and we need to come up with a conclusion because you're done with lab 4 and I'm correcting lab 4 and I can see that you did well. Also, the observation you have in lab 4 will not let you see all the parameters. You have a constant power supply and you have two identical bulbs. You can see that the voltage will actually affect the brightness. You can see probably that the resistance of your bulb will affect the brightness. So you will not be able to come up with a general conclusion due to the limited equipment that you have. You have a very simple circuit, that's why. So probably I would create a video for you to explain the whole thing, but I can summarize it quickly by saying the power is V times I. And if you replace V by Ri, it's gonna be Ri squared. And if you replace I by V over R, it's gonna be V squared over R. In other words, it depends on V and R and I. V is very easy to discuss because you would see V of the constant power supply divided equally in series, or V would be the same in parallel. R is easy to describe because you can see you have identical bulbs, so R for each, and if they are in series you have 2R, in parallel you have R over 2 for the equivalent connection. The current is the most difficult parameter to discuss because you don't know your constant power supply, how much current it is delivering. So for you to guess, you need to discuss the circuit as a whole and the R equivalent as a whole. So the best way to discuss the power, which is proportional to the brightness, is to discuss V and R. If you want to discuss I, you need to take your time to understand the behavior of I and it's a little bit tricky. Okay, did I make myself clear? So use power in terms of V and in terms of R. All right? Okay, shall we start with lab 6? Lab 6 is super interesting, super nice. Not difficult, it's a bit long, and the data analysis is not difficult as well. It's made of 4 parts, if I'm not wrong. So experiment 6, it's magnetic induction fields. You will be given a long solenoid, and I have all the rights. It's wrong. I'm sorry. I have all the right to modify this and to draw on it. So I'm gonna do it. So this is a long solenoid. You know what a solenoid is? Do you remember from high school? It's a long coil. And here you have a flat coil. So this equation is only applicable for a flat coil. And this equation is only applicable for a solenoid that is infinitely long. All right, they say the length is much bigger than the radius. It's like infinitely long because if it doesn't have, and this is at the center, And this is not at the center because it says a function of x. All right? Anyway, what are the 4 different procedures you have to do? You can see procedure, effect of length, then effect of current, then coil investigation. You see 3 parts. Inside the first part, which is effect of length, you have 2 cases. Repeat the same procedure for another solenoid. Let me explain on the lab report directly. So you will be given a solenoid. Do I have it here in the lab? No, because we put the equipment away. That was last week. This is a solenoid. Okay, I can show you in the video because I took the recording. The average diameter of the solenoid, let me show you on the video, fast forward. 1 second. Okay, so I'm gonna do this anyway to show you the solenoid because you will know what I'm talking about. This is the solenoid. So it's a long coil and you can see that something is written on it. Basically, the number of turns is 1000 and the maximum current it can take before it heats up and if it heats up, it would probably destroy the coil. And probably in the video, you can see how it looks like. And you can see that you have 2 solenoids. One is yellow and one is red, right? I want you to see the red part, this. You see? You see it has a certain length. You can measure the length with a ruler. And the average diameter is due to the fact that it's very thick. You see how thick it is? Let me show you. This thickness, so you have the outer, yeah.
This is the solenoid, the one in the box.
Yeah, this is the, exactly, you can see the red wires inside. You have an
out. Do you take it away or you leave it inside the box?
No, we leave it inside the box. You cannot take it out. But since the box is transparent, you can see through what's inside.
Oh, okay, right? Thank you.
So here they will ask you to measure the outer diameter and the inner diameter to find the average radius. But again, this is not an average, it's a mean or median. Like you know what I mean when I say average? It's not the average of many trials. So here, please don't do the RMS. It's basically 2 values you add divided by 2 to find the midpoint and the midpoint and find the diameter of the mid radius. Let's call it mid. All right, so average diameter of the solenoid, it's the midpoint to the midpoint. It's the diameter of the solenoid. The length will be given to you. The number of turns is written on the solenoid itself. Probably do this to keep the video next to us. Okay, no, this is so small, it's okay. Now I want you to look at the Tesla meter. What is a Tesla meter? Any idea?
Used to measure the magnetic field?
Yes, the Tesla meter is a measuring tool that is external to your circuit. I think here they show you the Tesla meter. So this is it. Let me move this away. Can I? Not yet because this video is not rendered. You see the probe? It's a black ruler. It's not a ruler, it's the probe. You will insert the probe in the solenoid and measure the magnetic field at each position. So do you see the probe? Let me show you how I do the experiment. It should be in the next video. So here I connect, by the way, the connections are very important. You have a triangle, you have power supply, you have an ammeter, and you have the coils. It's a triangle because everything is in series. And this is how I insert the probe inside the solenoid. So this is the Tesla meter. I show you how to switch it on and how to zero it. How do I zero it? I switch off everything current on my bench. It should give me 0 magnetic field. You cannot see the reading because it's dark, but I'm explaining in the video how I zero the Tesla meter by switching off the power supply. If it doesn't give me 0, I play with the 0 knob to make it 0. Then my job is to vary the position of the probe for every centimeter and measure the magnetic field inside the solenoid. Okay, you see the probe is going inside the solenoid at different positions. Let me explain. I'm gonna use this to be my x-axis. So this is my x-axis, right? I'm gonna take my 0 at a certain position away from my solenoid. This is around 6 centimeters. And this is around 6 plus 8, which is 14 centimeters. 14 centimeters, right? And this is around 20, just for you to have an idea of the order of magnitude. So as you move the probe inside the solenoid, you would see a very high magnetic field around this region at the center of the solenoid. So you will see your values increasing and then decreasing as you continue the table. The values will be given to you. Your job is to plot B versus X. So I expect you get something like that, okay? And this would be the midpoint or the middle line, the middle point of the solenoid. Do you understand where the 0 is? So the 0 is outside the solenoid because we wanted to see what's happening inside and what's happening on the right right side and the left side, okay? And then you have to repeat exactly the same thing with solenoid number 2. You will be given the length and the number of turns, and you repeat exactly the same thing, and you do the plot exactly, and you have to compare the two plots. The plot should be done on the same graph, so 2 graphs on the same plot. And then they want you to conclude. How do you compare them? Probably they have something similar and something different. So probably list the similarities and the differences. Yeah, I'm done with part 1. Now in part 2, you have to pick one solenoid, which is this one, for example, and you're supposed to put the probe in the center. So keep the tip of the probe at the center. And now you have to vary the current. Okay, back to my manual. You can see here, I'm sorry for scrolling fast. You can see here that the magnetic field is μ0. By the way, this is μ0 times N times I over L. L is the length, N is the number of turns. The length can be measured with a simple ruler. And I is the current. And remember, the I can be read on the ammeter, right? So if I vary the current, automatically B at the center would vary, and you see they're proportional, and you expect a linear relationship. So after filling in the table, you will see that you can plot, and you will see a straight line, and you can find the slope and the error on the slope. This is the only data analysis question you will face. From the slope, you find the number of turns. So again, what was the equation for B at the center of the solenoid? Anybody remembers? B at the center of the solenoid. Speak up if you remember the equation. μ0, yes.
N over Li.
N times I, because it's proportional to the
Over
current,
L.
over L. Yeah, which means if you ever plot B versus I, what does the slope represent?
Since μ0 N over L.
Yeah, that will be your slope. So you can easily find the number of turns from the slope and with the error on it. And then you compare the theoretical value of N to the measured value or the graphical value, and then comment means list the sources of errors. So this is the only section where you have to do a data analysis. Other than that, it's gonna be plot, description, compare, discussion, you know. Now for the flat coil will be a coil. Let me show you how it looks like. It's here, you see it? These are 2 flat coils. I'm gonna use only one, not both. I'm gonna repeat the same experiment as part 1, which means I'm gonna change the position. Let me show you the axis. This is my x-axis. The 0 will be taken inside because I can see what's inside. -5 will be 5 centimeters on the left of the 0, and +5 is gonna be 5 centimeters on the right of the 0, okay? And you will definitely see an increase in the magnetic field as you get close to the center and then away. Which equation do you use for the flat coil? You can use this equation, but take x to be 0 because x is the distance from the center of the coil. So if you are at the center, x is equal to 0. See what I mean? So x is equal to 0 at the center. In other words, this is x that I'm talking about. This is the x that I'm talking about, this one. Okay, compare the value of the magnetic field at the center, where x equals 0, to the theoretical value from the coil equation, and then comment. All right, I don't see this lab report to be long. I see it's very informative because you have two parameters. You vary the position of the probe, then you vary the current, and you do one at a time. So you keep the current fixed and you vary the position, or you keep the position fixed, usually at the center, and vary the current. And in the video, I show you the connections and the procedure to take measurements. I show you part A, I show you part B. This is the second coil. I show you how I do the measurement and vary the current. Let me see if it's visible. Okay, here I should put the probe exactly at the center. Okay, Akid, while watching the video, it will be easier for you to follow. But I don't want you to watch it with me because I know you're gonna watch it later. So you see the current. I also explained that the current, I decided to have a constant current throughout the experiment. Not constant when I need to vary it, but constant when I need it to be constant. Like for the solenoid, the orange solenoid, the red solenoid, and the flat coil, I'm gonna use the same current, which is 1 ampere. Okay? The series, you see that I can vary the current if I want. I can use 0.8, 0.9, 0.7, 0.6, 0.1, and do any measurement I want. I'm showing you how I'm varying the current, reading the magnetic field, while keeping the probe at the center. Okay? And that's it. I think the video will be clear enough. And probably I want to show you the flat coil. We're lucky we have a stand for the probe, so we can put the probe exactly in the middle. By the way, the probe measures from the tip. And you see the tip has two terminals, one that would measure BZ and one that would measure BX. And here you have a knob, the red knob, for BX and BZ. I'm gonna put the knob on BX because I want to move the probe inside and out. By the way, in this case, I'm not moving the probe. I'm gonna move the solenoid because it's easier experimentally, although it doesn't matter because it's relative motion that matters. You see how the flat coil is moving? And what's interesting about it, the flat coil has a ruler in here and it shows you the center of the coil, and you can read how many centimeters you're moving the coil. This is so nice and easy to handle. In the case where you have the solenoid, the long solenoid, you need a special ruler to be able to move your probe. Okay, and that's it for the experiments. So I'm gonna send you the video, and you have the manual. You have the recorded session of today, and I'm gonna send you some results, making them as clear as possible. You will let me know if you have some confusion, okay? And I'm not gonna keep you for a long time because I believe you don't need it. Any question? Yes? I'm gonna stop recording. I'm staying behind for the students